Hi everyone, this is Physics 30, Unit 2, Forces and Fields, Section 2, Magnetic Forces and Fields. This is Chapter 12 in your textbook. So there's a bunch of curriculum outcomes for this. You guys can read through these on your own. I won't take up video time for that, but there's lots to do with magnets and magnetic forces, magnetic fields, some people, Oersted and Faraday. So just read through these at your own leisure, and we'll go from there. Okay, below is a checklist of all the things we're going to be doing in Unit 2, Section 2. So Part 1 is magnetic forces and fields. Part 2 is moving charges in magnetic fields. Part 3 is current carrying conductors and magnetic fields. And Part 4 is magnetic fields, moving charges, and applications to technology. Okay, at the end of every section, we'll have some practice out of your textbook, and we go from there. Magnetic forces and fields. When we're done all the notes, we have the formative assessment. Remember, this is the one that is not for marks. Okay. After that, we have the curriculum review, which is for marks, as well as the magnetics quiz. And because this is the last section in this unit, we will have a unit exam at the end, and that will cover electrics and magnetics. So that is at the end of this section. Awesome. So let's get started. Part 1, magnetic forces and fields. Okay, so magnets are often magnets are objects, often metallic, that attract or repel other objects. But this attraction/repulsion is not caused by charges like in electricity. Instead, magnets have poles. In any magnet, there is a north pole and a south pole, which can't be separated. If you break the magnet, you get two smaller magnets, both with north and south poles, right? So if we break this guy up, smack, okay, well, we end up with two smaller magnets, so the north pole stays the same, okay, but then this smaller piece has the south pole there. The south pole stays the same, but oh look, this magnet has a north pole here. The reason for this deals with the alignment of electrons in the atoms of a magnet. This alignment is called a magnetic domain. Think of it as all of the electrons of an atom, or all the electrons of the atoms, are pointing in the same direction. So kind of like this. Now, please understand this is an extremely simplified diagram. But we can see that if we break the magnet at any point, the electrons will still be facing the same direction and then behave like two smaller magnets. Right? We break that, it doesn't change the direction of the arrows. Right? So anyways, we end up with north and south poles. Okay? Now, only certain metals are magnetic or affected by magnets. These are cobalt, iron, and nickel. Now, some compounds or alloys containing these metals are also metallic. Because these seem to be the only magnetic materials, it is thought that only these metals can form the necessary magnetic domains as discussed above. Now, there's 3 laws of magnetism. There are always 2 types of poles, north and south. Like poles repel, unlike poles attract. So 2 south poles will repel each other, 2 north poles will repel each other, okay? And a north and a south pole will attract each other. This isn't really new. We've talked about this before, but that's the idea. Now, of course, all magnets have both poles. You can't separate them. It doesn't work that way. Just remember the picture, the magnetic domains above. You always have the arrows or the alignment pointing in one direction, so you have north and south poles. Okay, so a compass, most people know what a compass is, but let's just double check. So a compass is a simple device that is used to detect magnetic fields. It consists of a small magnet that is pinned at the middle and is allowed to rotate around that pin. 2 typical models are shown below. Okay, so here in the first one, see the pin is here, and we have an arrow, okay, that points north. And really, as we spin the compass around, that arrow will always point to Earth's geographic north pole. Okay, In this style, in the second style, we have the two triangles, and it's the black triangle that always points north. All right, moving on. The interesting thing is that if a compass is a magnet and its north pole is attracted to Earth's geographic north pole, then there's two very interesting conclusions. One, Earth is a really big magnet. Okay, and two, Earth's geographic north pole has to be a magnetic south pole. Isn't that interesting? So if we draw a big picture of the Earth, okay, Earth has a south pole at our geographic north pole and a north magnetic pole at the geographic south pole. It's backwards. It's kind of crazy. But there it is. All right. A magnetic field, okay, is simply a region where magnetic effects can be observed or felt. It's a vector quantity, so it has both magnitude and direction. Okay, it's represented by the symbol B and is measured in a new unit called a Tesla. Okay, that's a capital T. The closer together the field lines, the stronger the magnetic field. So this was similar with electric forces and fields, right? The field lines, the closer the arrows or the bigger the arrows, the stronger the electric field. So it's the same way with magnetics. Okay, just with electric fields, magnetic fields have a direction, okay, and it is defined as the direction the north end of a compass needle points, okay, towards the south pole. Okay, remember, for electrics, we dropped a small positive charge and see which way it behaved. Here, we drop a tiny little compass and see which way the north pole of that compass spins. Okay? The other thing is dependent upon whether the field is inside of the magnet or outside of the magnet. All right. So, the magnetic field of a magnet goes out of a north pole and into a south pole. If you put a little magnet right here, okay, the north pole is going to be repelled by this north pole, and the south pole of the magnet, okay, of the little needle, will be attracted. So you can see the magnetic field goes out of a north pole. Same here, if we put a little compass right here, okay, the north pole is going to point away. Okay, so you can see how the magnetic field lines go out of a north. Now if you put a little magnet here or a little compass here, see, the north pole would be attracted to the south pole of that magnet. Okay, so the field lines go in to a south pole. Okay? Now when you have two magnets together, of course, we go out of the north pole and into the south pole. All right. So in this way, we can tell that these two repel, and then a north and a south pole, of course, attract. Okay, now, a magnet's kind of a funny thing. A magnet will attract itself. So if we have a south pole and a north pole, remember we go out of a north pole, so a magnet actually has field lines around it, because it does attract its own south pole. Sorry, north pole does attract its own south pole. Okay, we go out of the north into the south, okay, and we have a magnetic field that sets up this way outside the magnet. Now, inside the magnet, now hopefully this makes sense, but inside the magnet, if we go out of north and then into south for outside, then inside the magnet, we have to go this way, okay, to basically to complete the circle. Okay, we go this way. So inside the magnet, we actually end up going from south to north. So outside the magnet, out of north into south. Inside the magnet, the magnetic field goes south to north. Now, we're probably thinking, why is it a big deal? You can't really do much inside a magnet. Well, we can't do much inside a permanent magnet, but we can do things inside an electromagnet. So we'll get to that here shortly. All right, electromagnets. A current-carrying coil of wire that generates a magnetic field that can be controlled. Now, it's also called a solenoid. So electromagnets, another word for those are solenoid. Okay, the strength of the solenoid can be influenced by a whole bunch of things. Okay? Whoops, sorry guys. There we go. So it can be influenced by the current we put through the coil. Current, through the coil. Wow, I'm just doing great on this writing stuff, eh? There we go, that's better. So the current in the coil. Okay, so really what we're making, guys, sorry, I should probably draw this. So we're making, okay, loops of wire. Okay, so this is called a solenoid. Maybe you remember way back in grade 8, we wrapped some wire around a nail and made an electromagnet. Okay, so that was the idea there. So if we increase the current through this coil, okay, we can make a stronger electromagnet. If we increase the number of loops, we can make a stronger electromagnet. So if we just make a few more, okay, stronger electromagnet. Now, if we increase the size of the loops, we make a stronger electromagnet. Okay, now, just for interest's sake, both of these increase the length of wire. Okay, means more wire. Okay, and the last one, okay, if we change the core of the solenoid, okay, so basically what we can do, we can wrap this wire around and not just wrap it around the air. Okay, so if this is hollow, it's called an air core solenoid. Okay, and it can be a decent electromagnet. However, if you wrap this around like iron or nickel or one of those ferromagnetic substances, okay, your electromagnet will be much, much stronger. So if you have something in the middle, okay, that's called the core. So if you can have like I said, you can have the air core, okay, and that makes it decent electromagnet. But if you have a core of iron, say, that is much, much stronger. So changing the core of the solenoid makes the electromagnet stronger. All right, let's talk about some other causes of magnetism. In 1820, Hans Christian Ørsted, okay, discovered that there was a relationship between electric current and magnetism. His discovery came by accident when he was doing an experiment on the newly developed electric cell. Okay, those are just batteries, remember? Okay, and he noticed that the electric current caused a deflection in a compass needle. Now, this could only be explained if the current-carrying wire act as a magnet, right? Because, hey, compasses are affected by magnetic fields. So, the wire itself, okay, without the current, didn't make the deflection in the compass. It was only when the current was on that it deflected the needle. Okay, so again, another discovery made by accident, but he was smart enough to understand what was going on. Hey, the compass moved. There's got to be a magnetic field here. Okay, Now, in order to show kind of what's going on here, we need to have a new notation. Okay, so this is a cross section of a wire, this little circle. So basically, you can think of the wire here, kind of in 3D going wherever. Okay, now, if you picture yourself shooting a bow and arrow, okay, if you shoot the arrow away from you, all you really see are the tail feathers. So that's the X. So the X is the current going away from your eyes or into the page. Into the page. Now, this next one's a little morbid, but if you are getting an arrow shot at you, okay, all you really see is the tip of the arrow as it's coming. That's kind of what you focus on. Okay, so this little circle, that represents the tip of the arrow, so that is the current coming out of the page. Okay, so now, this new notation, so X going into the page, the dot coming out of the page, that is the current or electron flow in the wire. Okay, so now look, if you imagine the wire coming out of the page, okay, so the X is current moving into the page as shown in the diagram. The dot means current coming out of the page. You already said that. So look, here's a better 3D diagram. So here's your page. Okay, so the X means the current is going away from your eyes. So you basically have to look down on it. So there's my little eyeball there. Okay, so you're looking down. The current is going away from your eyes. So here, you're looking at the wire, and it is coming out of the page. Okay, coming towards you. All right, so there's some new notations that we can use to describe some of these effects. Next page. Okay, so using this new notation, it's now possible to define the direction of the magnetic field around a current-carrying conductor. Okay, so here the X, the current is going into the page, okay, and what ends up happening is that the magnetic field, it goes around the wire, okay, like that. It makes a circle, okay, and that circle, now here's the crazy part, circles never start and stop. However, we say that the magnetic field goes counterclockwise. Okay? For the dot, for the electric current coming towards your eyes, okay, the magnetic field goes clockwise. So north to south goes this way. Okay, and I'm going to show you how to use this here right away. Now, remember the magnetic field always goes north to south. It is possible simply just to memorize these things, but there really is a better way. Okay, so left hand rule number 1. So we use our left hand. Okay, now our thumb points in the direction of the current. Okay, so either into or out of the page, and then we wrap our fingers around the wire. Okay, the curl of your fingers represents the direction of the magnetic field. Okay, so let's just try that with our pictures up above. So, using our left hand. Okay, left hand. So our thumb would point into the page. So thumb into the page. Okay, and you can see how your fingers wrap around this way. Okay, now the orientation of my fingers, it kind of goes like this, but the thing is that's still counterclockwise. Okay, awesome. Now, if your thumb, for the next picture, your thumb points up towards your eyes, so your thumb is out of the page. Okay, so your thumb points out, and then again, the orientation of my hand, because I don't want to twist my wrist too much, goes like this. Okay, so that is going in the clockwise direction. Okay, great. Now, if a compass is placed beside either of the wires above, the compass needle will align so that the north pole of the compass will attract the south pole of the wire's field. The field is now a circle that never starts or stops. So how does it have poles? Okay, this can be addressed by placing a north pole wherever we want to start and a south pole wherever we want to stop, as shown above. See, so if I start here, that's where my north pole is. I stop there, there's where my south pole is. Now, we're going to do an example so this will make a little more sense. Okay, practice problem number 1. A wire is carrying current as shown in the diagram. If a small permanent magnet, so like a compass needle, is brought near to the wire, as shown below, will the magnet be attracted or repelled by the wire? Okay, so we use our first left-hand rule. There's the X, so our thumb points into the page, and our fingers rotate around this way. Okay, great. Now, here's the thing. On the circle, we want to draw, okay, so here's the circle, and it's going this way. Now, what we're going to do is we're going to set up the tangent line, see, right there. So that's the tangent line to the circle, and that's basically where we're going to start and stop. So if you look, the arrow comes around, so here's where I'm going to start. So this is going to be a north pole, and then come around to here, so this is going to be my south pole. Oh, neat. So we always draw the magnetic field in the wire kind of at that spot where it's going to be closest to the permanent magnet. Okay, so we end up with, oh look, a south and a north here, north and a south. We are going to attract this magnet. So the wire will be attracted to the magnet. Okay, so that's kind of what I explained down here. First, draw the magnet around the wire using the left-hand rule. Thumb points into the page. Use our fingers to wrap around. Okay, and then we draw this tangent line. Okay, north, south, they attract. Perfect. Okay, once the field is drawn, we simply label the north and south poles, okay, meaning lined up next to the permanent magnet. Okay, so next we see if the magnets attract or repel. In this case, they attract. Yay! Okay, so what does all this mean? Diploma questions around this concept deal with the direction of the field around the wire or the magnetic interaction between two current-carrying wires. Okay, so if we look at example 2, two wires are carrying electric current, so electron flow, as shown. What is the direction of the force felt by wire number 2? Okay, so I want to know which way wire number 2 is going to go. So if we look at these things, we, okay, wire number 1, we point our finger point our thumb into the page. So our electromagnetic field goes around this way. So look, they're going to interact here in the middle. So this is where the interaction between the wires happens. So we draw the magnetic field coming around this way. Oh, look, so this is kind of where I want. So this is my north. This is going to be my south. So again, you can draw the tangent line if you want. Okay, so there we go. Now, drawing the second one, your thumb comes out of the page and your fingers wrap around this way. Okay, so they come this way, and then we start here. So from north to south. Oh, wait a sec. Hey, the south poles line up, the north poles line up. So these two wires are going to repel. That means wire 1 is going to go this way, and wire 2 is going to go that way. Well, the question asks for the force felt by wire 2. So wire 2 is going to go to the right, or answer C. Okay, so here's that explanation down there. Okay, so number 3. Okay, so little things or questions like this. So if I put compasses all the way around the wire here, okay, only one of these is going to be set up properly. So which compass is properly aligned with the magnetic field of the wire? Okay, so we put our thumb out of the page and we wrap around this way. So this way, around, around, around. Okay, so if we make a tangent line there, okay, so that's north to south. So we can see right now that north should be this way, attracted to the south pole of the wire. Okay, so it's not B. Okay, so if we look at A, okay, there's the tangent line there, so north to south. Oh, look, that north is going to be repelled, so the compass is going to be repelled by this north, so no. Okay, again, we go this way, so north to south. Oh, this needle should be pointing this way. Okay, so not D, so it's, hey, it's got to be A. So if we look at that, okay, so there's the tangent line. Okay, so then north to south. Oh, look at that. The north pole is lined up to the south. So that is the direction the compass needle will point. So I'm going to erase a bunch of this just so it's not quite so messy. Okay, let's just draw that one more time for you. So it comes around like this. Okay, tangent line, north, south. And oh, look, the north pole would be attracted to the south pole of the wire. Okay, and that's the way it lines up. Okay, so that's just a little simplified, but again, if I would have started with A, I wouldn't have had the rest of those pictures. So there you go. Okay, now solenoids and left-hand rule number 2. All right, moving on. Okay, so if the wire is wrapped around so it makes a coil with a large number of loops, a solenoid may be produced. Okay, remember, solenoid is just a fancy word for electromagnet. In physics, the term solenoid refers to a loop of wire which produces a magnetic field when an electric current is passed through it. Okay? All right, so often this wire is wrapped around a metallic core, but it doesn't have to be. Hollow air core solenoids are also possible. Solenoids are important because they can create controlled magnetic fields and can be used as electromagnets. Okay? In a solenoid, the magnetic field is strongest inside the coil of wire and weaker outside the coil. To determine the direction of this magnetic field, we follow these rules. Okay? So basically, left-hand rule number 2. Okay, this left-hand rule works by wrapping your left hand around the coil of wires so that your fingers wrap or curl in the same direction as the current in the wire. With your fingers aligned like this, if you stick your thumb out at 90 degrees, that's going to be the north pole of the solenoid. Excuse me. Okay, now, remember you have a battery. Batteries have positive and negative terminals. Electrons come out of the negative end. Okay, so if we set up the battery like this, now remember, there's another way for a battery. It's these short and long sticks. Remember, the shorter ticks are negatives, longer ticks are positive. Okay, so a battery would be set up like that. You need to know both notations. Okay, so the electrons are coming this way. And if you notice, we start the coil wrapping kind of on top of the loop and then rotates in behind. I think I've done a decent job 3D'ing this. Okay, so you basically put your left hand flat on top of the page and then your fingers wrap around the wire. You can, if this little tube thing, if you put your pencil out and wrap around the pencil, you can kind of get an idea. Okay, so this, of course, you stick your thumb out, and that points to the north end of the solenoid. Now remember, outside a magnet, the north, the electric field comes out of the north and into the south. Now remember, inside the coil, now, if this is a piece of iron, you can't really get inside, but if it's actually hollow, then you could put something in there and the magnetic field would be going from south to north inside the coil. Okay? Outside the coil, it behaves just like a normal magnet. Okay? Either way, you get something set up like that. So, you can see my picture of my hand there. Okay? Your fingers wrap around, your thumb points to the north pole of the electromagnet. Wow, hey? Crazy. Okay. Magnetic fields are just one more part of field theory, which can be used to explain gravitational, electrical, and magnetic phenomena. In the table below, list the source, direction, okay, so the attraction or repulsion, and the range for each type of field. Okay, so gravitational. The source of gravitational fields is mass. Okay? Gravitational fields are always attractive. Okay? Now remember, this is that formula from Physics 20, Fg equals big G m1 m2 over r squared. Now, as r increases, the force gets smaller, but there's no limit to r. So this is infinite. Gravity acts at any distance. Okay, so electric fields. Okay, electric fields, the source of those is electric particles. Okay, so electric charges. Okay, now, the funny thing about electrics, it can be attractive or repulsive. Or repulsive. Okay, now remember the formula for this, it's Fe equals K Q1 Q2 over R squared. Okay, so again, as the charges get far apart, the force gets less, but it's still infinite. Okay, and lastly, we have magnetic fields, which of course are caused by moving charges. Or permanent magnets. Okay, this can be attractive or repulsive as well. Or repulsive. Okay, and magnetic fields are exactly the same as the other two. They act at infinite distance. Okay, awesome. So there's a whole bunch of theory for you. I want you guys to practice this material by doing section 12.1 in your textbook on magnetic forces and fields. Okay, that starts on page 592, and I want you to do those questions. So number 2, 6, 7, and 8, okay, 10 and 12. Remember, you can go right out of your textbook, or I have put that page in the workspace so you can print it out and write all over it. It's totally up to you, whichever you want to do. Thanks, guys, and we'll see you in next part.